Yeah.
Okay, we're gonna get started on Lab 11. It is a MATLAB lab.
I forgot to turn this English.
Why is that funny? I don't know. But it is. And we're gonna play around with complex numbers, and so basically, test 4, which is not this Friday, but in 4 weeks, is going to involve a lot of complex numbers. So this lab is really designed to get you comfortable with that and well-versed in how they work, not just in MATLAB, but also, on your own calculator. You might try some of these things. There are some interesting peculiarities in working with complex numbers you should be aware of on your calculator. In case you do that. So the basic lab is going to be that we're going to perform arithmetic operations on complex numbers. and then, as we've been talking about this week in the previous 2 lectures, also on Friday, we're going to learn how we represent sine waves as complex numbers. We call these phasors. And then towards the end, we're going to calculate complex impedance and admittance of circuit networks, and then we'll be plotting also 2 sine waves on the same plot, so you can kind of see how that works. So I'm just going to run through this up front at the beginning. We can kind of flip through this together, and then I'll just leave you all to your devices, and I'll walk around. And if again, I like the idea that we can kind of record your progress or issues that you're running into for people online. I think that's very helpful. So in MATLAB, we tend to use, you can use I or J for the square root of -1, but tend to be using J for circuits. So you can define a complex variable z equals 10 minus 12j, like that. And this is the one thing that can kind of screw you up if you're not careful. The order of operations when complex numbers are involved. If you say 1 over 2i in MATLAB, that equates to minus 0.5i. And you might think that's a half I, where the I is in the numerator, but in fact, it's 1 over parentheses 2i, because the I sticks to the 2. And it does that before it hits the division operation. Does that make sense? And 1 over something with I in the denominator is negative, because you got to multiply by I over I or j over j. And that gives you a -1 in the denominator, and that puts a negative there. We kind of did that in lecture 2. So that can screw up a calculation pretty easily. If you really want, on my calculator I don't have it with me. It's a Casio FX115. Anyone have one of those? Those are pretty decent. They have a complex number format that you can enter in. It makes it real easy to represent. When I type in 1 over 2i, it evaluates to what I would think is 1/2 I, because the value of I is secondary to the division operator. So those little things can be a bit of an issue. I'm using this less than symbol to represent phasors. And in other words, that's the phasor angle. So if you talk about a phasor 10 with this less than sign 45, what you should read is that's something with a magnitude of 10 and an angle of 45 degrees. Has anybody not seen the lectures yet on what we're doing at all? Is anyone completely lost here? Because I could give a little preview here. You should familiarize yourself with the last 2 lectures that we went over this week. So we can create the rectangular form of this polar representation of a phasor by saying 10 times cosine d, because we want cosine in degrees of 45, plus j times 10 times sine d of 45. That gives you a complex number. And also want to make sure you use sine d and cosine d for that phase angle, which is in degrees. You can multiply these together. You can add them together and come up with different numbers. You can calculate. So this is basically showing you how you can go, and this operation is basically going from a polar form to a rectangular form, which is how MATLAB normally likes to represent complex numbers.
We should, on MATLAB, generally try, if we have a polar number, convert it to a rectangular.
Should you normally convert it from polar to rectangular? If you're going to do any kind of arithmetic on it, it will happen as you enter it in, because you sort of have to enter it in, because you have to actually enter it in as a rectangular value.
Okay, so we won't be entering any like distance, angle.
No, I have a function. I'm going to show you that, I think, next week, which is going to make it a little bit easier. But for now, I kind of want you to get used to this kind of thing, because this is how you'll have to, generally how you have to do it on your own calculator. If your calculator doesn't support complex numbers, you'll have to sort of do these things yourselves and do the bookkeeping. And if you want to go back, so if you end up with a complex value in rectangular form, you want to find the magnitude and the angle of it, convert it back into polar form. MATLAB does that too. There's the ABS function, which is the normal absolute value function, which works for, you know, real numbers, but it also works for complex numbers and gives you the magnitude of that complex number. In other words, it gives you the square root of a squared plus b squared if it's a plus bi. And the angle function gives you the angle in radians, and it is a 4-quadrant angle, like I mentioned in lecture, you know, because the tangent, the arctangent function, if you just use the arctangent, here, let me show you this. I got to show you this. It's really... preferences, font. Yes, I want my font to be readable. So, you know, so if you say, like, you know, z equals 10 times cosine d of 45 plus j times sine d of 45, you're going to get this complex number, right? And if you say ABS of z, you're going to get the, whoops, I messed it up. Z is supposed to be, that's another thing you could easily forget, right? You got to be really careful when you do these things. It's really easy to mess them up. Got to be, pay attention, right? It's 10 times cosine, so this is the magnitude, right? But I also have to do the magnitude on the sine part too. And then when I do the absolute value, that gives me the magnitude, which is 10 of that number, right? And when I do the angle of z, that gives me the angle in radians, which I could then multiply times 180 over pi and get the original angle that I started off with back, right? So that's going from rectangular to polar, and then back, polar to rectangular, and then back into polar again. Now the thing that I was about to talk about is this idea of like if you're using your calculator, right? Suppose you end up with a complex number that's maybe it's let's call this W, and maybe it's minus 3 plus 4i, right? Now, you know, the angle, this phase angle, is where the, do I need a picture? I kind of need a picture, don't I need we can't talk about this stuff without some kind of a diagram. So where is that complex number? Minus 3 plus 4i. Well, it's going 3 over in the real axis and up 4 in the imaginary axis, right? Right over there, right? And you know you have an arctangent, and as we've talked about, you know, the regular, you know, if you're at 10 and 10 and, you know, 45 degrees, you know, the angle is the arctangent of b over a, right? But if you just plug in the arctangent of b over a in your MATLAB command or in your calculator, if you say a tan d, and we can do it in degrees, right, of 4 divided by minus 3, right, that's b over a, it's going to say it's negative 53 degrees. Is that correct? That's telling you that it's over here at negative 53 degrees, right? Isn't this negative 53 degrees? That doesn't seem right, right? What's the problem? Am I losing you guys? Should I say that over again?
Is this what you were talking about yesterday?
Yeah.
With the 4-quarter?
The 4-quadrant, yeah, so the normal ATAN function on your calculator, arctangent, inverse tangent, it's the inverse tangent of a number, right? And that number isn't enough information for it to know which quadrant you're in, so it assumes that you're either in quadrant 1 or quadrant 4. You do the arctangent function on your calculator. These are like really common pitfalls when you're working with complex numbers and you're trying to go to angle, right? So be aware of that. The angle function actually works correctly. If you do the angle of W, it's going to say it's 2.214, right? You take that and multiply it times 180 over pi, and it's going to tell you that it's 126 degrees. That is the correct angle, right? It's 126 degrees. It's obviously going to be more like that, right? Because here's the number here, where this is, -3, and this is 4. It's this angle here, which is about 126 degrees. You probably agree, right? That seems more like it, right?
Yeah.
Now, if you're stuck with your calculator and you only can do the arctangent that's in that 2 quadrant, you either got quadrant 1 or quadrant 4, you have to realize you might have to translate that into the correct angle yourself on your calculator, right? And to do that, you have to add basically 180 degrees.
Yeah.
If you know you're in the wrong quadrant, it's going to be 180 degrees off. The other option is if you have a value like x equals, if they're both negative, -3, -4i, then again, your arctangent function on your calculator is going to be the same as arctangent of 4 over 3, right? It doesn't know that both of these guys are negative because it's doing the division first. So it's going to think you're at 53 degrees. Again, adding 180 degrees will correct the quadrant there so you have the right answer. Questions on that? That's just, I'm pretty sure maybe you kind of stumbled on that already, but it's probably somewhat new to you guys. So in the first part, there are some exercises. Let's see, where are these drill exercises? There it is that. Let's go ahead and open. I always meant to have some answers here. I think I can probably pull up the answers from last year. So you're going to do these drill exercises in part 1, which is basically just doing some complex arithmetic and checking your answers. Try checking it on your calculator. As we do in a lot of engineering, we want to sort of make sure that our models are correct. We try a couple different ways to get confirmation of what we're doing. So that, why am I not seeing that thing there? But okay. And so a few values you're gonna do some operations on. Here's A, here's B. Going to calculate that into rectangular form. And just do some arithmetic with that stuff. Now, part 2 is where we're going to start working with phasor transforms, and that's the idea that you could take a sine wave and represent it as a single complex number. A sine wave is essentially, some Vm cosine omega t plus phi, and what we're doing is we're saying, well, we could represent that as the real part of some complex value using Euler's identity, e to the j phi equals cosine of theta plus j sine theta, and you can basically say, well, we just want the real. If we just took the cosine part, then we would have basically a cosine of that phase angle. Just took the real part of that complex value, and there's our cosine thing. And what we do with the phasor transform is we kind of throw out the e to the j omega t part, because that's just sort of a constant revolving phasor going around and around in a unit circle, not giving us a whole lot of information. But this e to the j phi gives us a lot of insight into the phase angle of that thing, which helps us later when we calculate power and stuff. And so we call this boldface V the phasor transform. That's what that P is, of a sine wave. And this boldface V is a complex number. And you get it just by doing, Vm times the cosine of phi plus jVm times the sine of phi. Okay, with me so far? Am I going too fast? And then the inverse phasor transform is if you have a phasor thing, which is you represent it as a polar form, and you want to get back to the cosine, you add the omega t back to it, and you just keep that phase angle. So here's a process. Suppose you've got a sine wave of omega t plus 10 cos omega t plus 45 degrees. And you want to add it to another sine wave that's 5 cosine omega t plus 60 degrees. We've got to find v equals v1 plus v2. If you had to use trig identities, that would be a really difficult thing. But with complex numbers, it's really easy. You just take the phasor of first one. So this is v1. I probably should use capital V1 to indicate that it's a phasor. But here you are. This is a complex number with the magnitude and the phase angle of this v1 sine wave. And then v2 is the same thing with the v2 sine wave. And you're doing this in the complex domain. You're adding those two complex numbers together to get the result. And then you take the inverse phasor transform by finding the absolute value, the magnitude of v, and the phase angle of v, which is the angle times 180 over pi. And that gives you the result, which is 14.8, the magnitude you figured out, cosine omega t plus 49.9 degrees. You just added two sine waves together in the complex domain. Now you got the result, you know the phase angle and all that stuff. So in part 2, you're gonna mess with some of these things, calculate those guys, and then in part 3, this is where it got cut off a little bit. This is where we apply this to actual circuits, and we develop these relationships in class where we talked about this thing called impedance in lecture yesterday, where the impedance of an inductor is like the resistance of an inductor at some frequency omega, and it's j omega L. The impedance of a capacitor is like the resistance of a capacitor at some frequency. It's 1 over j omega c or minus j over omega c. And you have this table here which kind of summarizes these things. And what happens with these is that you can now, if you know the complex impedance of something, and this is actually, I may have to, if you could write this on your handout maybe, and this is something I should probably put on the handout because it's a little bit new for you guys, and I know it's kind of a little confusing, but let me just sort of sketch out what I mean here. So for this circuit here, if we want to find V out of t, and we know that we've got a V in of t with a 4 cosine omega t plus 10 degrees, maybe we want to find I of t, maybe we want to find V out of t. Here's how we do this. This is the process that you're going to use in the last quarter of the class, starting on this week's homework, to solve circuits now in the AC domain with sinusoids. So you can represent V in as as a phasor, right? It's going to be some 4 angle 10 polar form of a complex number, right? You're going to represent as a in MATLAB, you're going to turn that into a rectangular form. It's going to be 4 times cosine of 10 plus j times 4 times the sine of 10, right? And that's your V in phasor, right? This is a phasor. So we just did a phasor transform of V in of t, right? Okay, does that make sense? Okay, and we look at this network, and oh, they have to tell you. Oh, here we go. Assume. Well, it looks like my handout needs to be fixed here. That with a. Am I viewing this right? Let me download this one. Sometimes the viewer gets a little messed up here. Yeah, it looks like it's definitely got some stuff chopped off there. Note that with f still equals 60 hertz, or So when f equals, so we're going to assume basically that this is a 60 hertz sine wave, and 60 hertz means 60 cycles per second. And when f equals 60 hertz, what's omega? Omega, omega equals 2 pi times f, right?
So 125?
It's more like 377 or something. 2 times pi times f, right?
377?
Yeah, 6 times 60. 2 times pi times f, right? Did you forget the pi?
120 times 5. Yeah, 377.
Yeah, 377. So 377 radians per second, right? So the key when you're looking at a circuit, you got to know what the frequency is, and omega is just hidden here. I should put that down. But so you know omega, and as we learned in lecture, what's the impedance of a resistor?
It was R, right?
It's just the resistance, yeah, and that's going to be 1,000. The impedance has the same unit of resistance, but it's a complex number. What's the impedance of an inductor? It's on your handout. It's on my display at the very top. You can see it. Inductor, J omega L. And the impedance is the complex number. The reactance is just the imaginary part of the complex number. So J omega L, is that too small? Make it bigger. Right? So ZL is going to be J times 377, because that's our omega. And what's our L?
2 millihenries.
Times 0.002 for 2 millihenries, right? So that's an imaginary number. And our ZC is going to equal, it's 3 microfarads. So that's going to equal, let's put here J omega L. So this is minus J over omega C, and that's going to be minus J over 377 times 3 microfarads is 3 times 10 to the minus 6. And you know in MATLAB, you can represent that as 3e minus 6. So whatever that is, you're going to get an imaginary value, right? Now, if these were all resistors, what famous circuit is illustrated here when we're trying to figure out V out relative to V in? What famous comes up over and over again in this class? There's a voltage divider, right? And if we just knew those resistor values, we could use the voltage divider formula to find out what V out is. And the thing is, we now know those resistor values because those resistor values are the impedance values of those elements. And they add and they go in parallel the same way resistors do. So we can find, using the voltage divider formula, or just, the series in parallel, series impedances add like resistors. So Z total is going to equal ZR plus ZL plus ZC. That becomes one big, hairy, complex number, which has just got one real and one imaginary part, right? And then knowing Z total, we can use the voltage divider formula to find V out. So V out equals V in times what? What's the impedance of the capacitor?
What's that,
ZC, yeah, we'll just call it Z. You can make variables here, or you can just type them in directly, but it's nice, it's convenient to work with variables. It's kind of, in MATLAB, it's really good that way. So you can define ZC like this, right, and then just use ZC and divide it by Z total. It's the impedance of the capacitor divided by the impedance of that whole network. Make sense?
Mm-hmm.
Sure. And what you get is a complex number, right? And then if you want to get V out of T, it's going to be converting that complex number back into its magnitude and phase angle, and then constructing a sine wave, a cosine with that. Okay, questions? Maybe we'll take that up when you get there. I'm sure you'll have questions when you actually get into it. And yeah, so that's the basic idea. This is kind of showing you the logic behind it. And you get a few more of those to try. And there's 2 more if you have time or interest to do those. But this just kind of get you kind of a big picture of what's happening here. I mentioned actually that I was supposed to show you how to plot 2 sinusoids with different phase on the same plot. And I think that might be helpful to see that. So maybe at some point I'll take a break and show you that as well when we get there. But I'd like you to try to tackle these things first. One more thing, there are some pitfalls I remember in the lab here. Just be careful when, like when they're asking you to, like when they have a sign here. When did it do that? When they have a sign here, the phasor is really wants the sinoid to be put into a cosine. And we have to sort of keep a consistent cosine basis for the phasor transform if we're going to do any like adding of different phasors together. If they're all going to be sines, you can do the phasor transform without worrying about that. But if you're going to mix like some with cosines and some with sines together, you got to convert the sines into cosines. And you remember how to do that? There's a 90-degree phase shift. Do you know how to do that? You might want to do this also. Put this also on your sheet. It's a little mnemonic you can use, or a guide, right? Which I use all the time, which is basically to go from cosine to sine. Let me make a bigger pen here. This pen's a little bit too small. So cosine to sine and vice versa is, anyone can draw a cosine because cosines start at 1, right? And sines, so this is the cosine, and sines start at, sines start at 0, right? And you can see, well, this point here, when we're at 90 degrees, is the same, essentially the same point on the curve as this point when we're at 0 for the cosine, right? So, you can put this on your cheat sheet for test 4, but you can pretty much derive that cosine of 0 has to equal the sine of 90. And so, if you have, cosine of, theta is going to equal the sine of theta plus 90, right? If theta is 0, you got to be 90. If theta is 90, you got to be 180 on the sine, right? And so you can use that to shift back and forth. You could also say then that the cosine of theta is the sine of theta plus 90, but that means the cosine of theta minus 90 would equal the sine of theta, right? So those are the way you can transform back and forth between those. So put that on your lab somewhere where you can hang on to it. It can be helpful. I think that covers everything, but I'm sure stuff will come up, so just let me know. And have at it and have fun.
One question, but is AB 8 times B?
Yeah, that's A times B.
Okay. Just curious.
Yep.
So it's asking for A plus B, and I just did A plus B. Is there anything else I should do? I had the entered values that it wanted me to do for A and
That's a
B up
weird
here.
sync problem going there. Oh, that's weird.
Because like A and B were already in rectangular, and it wanted me to give
Yeah.
the rectangular sum. So it is just A plus B there.
Yeah, that's
right?
good. Yeah, later on it's going to get a little more complicated.
Yeah,
'cause
like
you got to convert stuff into rectangular. Yeah,
Yeah,
that's good. Mhm.
yeah, okay.
Yeah, that's
Just
fine.
making sure.
Just to kind of record your work.
And just to double check, so if I'm finding, I think it was up here, I found that my angle, I want to try and find it. I think, yeah. So I found here that my angle, crap, it's not there. Well, if I find out my angle is negative, then that means that since I'm taking the arctan, I need to add 180 at the end, right?
No, angle is okay.
When-
If it's negative, you're okay. But it's when you're using you have to. Well,
when is it that I add 180 then?
when you know which quadrant is, but you have to sort of know based on the values of A and B, the real and imaginary part, which quadrant it's in.
Oh, I see.
If
so
both
when
if
it's
both of
not-
them are positive, you're in quadrant 1.
Okay.
If one of them, if the A is if the real part is negative and the imaginary part is positive, you know you're in quadrant 2.
Okay, so if it's in 2
If you
and
get a
3, that's
negative
when I add
number,
180.
you've got to convert a negative value into quadrant 2 by adding 180 degrees. But you got to apply your own knowledge about where it's supposed to be.
Okay, A is my real axis and B is my imaginary axis.
Yeah, yeah.
What does it matter? If they're opposite, then I have to add 180 at the end, right? To the angle. If they're opposite signs, because they wouldn't be in quadrant 1 or quadrant 4.
It's a little more complicated than that. Let me got a piece of paper and pen? Yeah, let me write it out here.
Yeah, sure.
So, like, when you have, do it over here. When you have, the value of, z equals 4 minus 3i, right? You plot that like a Cartesian coordinate, okay, 4 minus 3, okay, so 1, 2, 3, 4, down 3, right? So you're right over there.
Mm-hmm.
Well, again, and you only have to worry about this when you're using your calculator, because MATLAB's angle function is going to always put it in the right quadrant.
Oh, so should I never add 180 on MATLAB?
Not in MATLAB.
Oh.
But in your own calculator, if you're doing it, on the fly, or you've got an ATAN thing, then you got to do that transformation.
Okay.
But the angle function is always going to put in the right place. But you can always check, because you know that a real part that's positive, imaginary part that's negative, should be in quadrant 4, and your regular ATAN function that's going to give you that on your calculator.
Okay. That makes it easier. MATLAB.
It's going to be the ATAN of minus 0.75. Is going to be whatever. It's going to be this negative angle there.
Okay.
But if it was the other way around, if z was minus 4 plus 3i, if you're using your calculator's ATAN function, it's still going to think it's minus 0.75 because 3 over negative 4 is the same as minus 3 over 4. And so that one you have to add 182. But you got to apply your own little understanding of where it's supposed to be.
And when I'm converting my my things to rectangular, so my omega here, my frequency factor,
Yeah.
that doesn't look like it's coming into play. Like
It doesn't come into play.
Yeah.
No.
And,
For the phasor transform, you just throw out the omega.
Okay, and
You
and
use
when
it if
we're-
you're calculating impedances, but you
Okay.
don't use it for the phasor.
So when I'm transferring between so I should assume here I have no omega then for these three since I'm going back to rectangular.
Yeah, so you just put omega in your answer. See, like here's an answer there which has an omega in it.
Okay, that's pretty easy.
Mhm.
All right, no
Yeah.
problem.
Any other questions? Questions, guys? Okay. Questions? Okay, okay?
I was just wondering if I did that correctly for that phasor transformation. Did I? Is that in the right form?
So C.
Yeah, for C.
So you converted. That became 5 angle 36, right?
Right. So I those are all my calculations.
Yep. So that's 5 in rectangular form, 10 minus 3. Yep. You add them together. You find the magnitude, and you find the phase angle, and so that's the answer. Yeah.
And then I leave it as a trigonometric function as the phasor transformation. Or do I have to convert that to the polar form?
No, for 74, it should be polar form.
So
For 70 or 7.4, 7.5, it is you're going to do a time domain, so
now
the
you-
answer is like going to be like that.
So now I convert this to polar.
So yeah, all your answers should be something like a magnitude within a phase angle.
Okay.
And you can use the less than sign to indicate the phase angle.
Sine here, do I need to convert that to a cosine by adding the angle, or can I still just do the cosine, the 10 times cosine 20 plus 10 times sine 20?
No, if it's a sine, you should do the phase shift first.
So I do need to do the phase
Shift
shift.
it back into a cosine
Okay, that's fine.
using that relationship. Do you have that? Using this one, you did that, right?
But that's easy because that's just 90 plus 110.
You subtract 90.
Oh, subtract 90. Okay, so let's see.
So yeah, you should write that down.
382, 90.
It's so easy to mess up. So you should do that picture, and the logic of it is really useful if you don't have
Oh,
formula.
so yeah, no. So I knew that. My problem wasn't like for this one. I converted that sine into the cosine with the phase shift. All right, you get the picture. I converted.
Awesome.
Yeah, I converted this one to make sure I add them, but I only thought I had to convert to make sure they were the same trig function.
Yeah.
So for this one right here, I just wasn't sure if for the formula to work at all, they
Yeah.
always had to be cosine.
Well,
now I know.
yeah, you should. I mean, if you're
So rule
you're
of
doing
thumb-
anything with I, no, but
yeah.
like certain circuits will have, they'll ask you, or they'll show you that your source is a sine wave instead of a cosine wave, and so you either convert it to a cosine or just keep everything as sines, and when you're done, you're just going to express your answer as a sine.
So
You
for
know.
a good rule of thumb though is just pick a sine and decide to stick with it. And since most of these are cosines, I'm just doing cosine all
Yeah.
the way. Okay.
Yeah.
I think it's a question since I've already taken linear algebra, but so you see how there's a negative 100 factor there?
Yep.
Yeah. Would it be perfectly alright in saying that this is a negative 100 times that minus that? Let's like the same thing as that, like adding that, but that's negative 100, and then just adding these two to get b sub d. Or,
Yeah, so you can represent a negative sign as a 180 degree phase shift. That's the other thing you could do.
Oh, that'd be awesome. Too.
But you can also
No, from the thing that's in
you can also subtract. That works as well. I mean,
Yeah.
if you have the negative on the phasor, that will work too. Is that what you're doing? Which one is that?
That's what I'm doing is I'm already just adding the negative number, just adding it, just the same thing as
So
subtraction.
yeah, so you convert that, but you did convert it to you did a phase shift for cosine, right?
Yeah. 120 and 120. That's 90 plus
Can I see that
30.
whole problem? I'm not seeing the whole thing. Maybe you can close that navigation thing.
Oh yeah. Why is it there? There we go.
So the minus 53 cosine. Wait, is it C you're doing or D? D, right?
D.
D. Okay, so it's plus 30 and 1 and plus 4. Yeah, so that sine would be turned into a cosine. What did you shift it to? D2. You had it 120?
Mm-hmm.
You added 90 to it?
Mm-hmm.
I mean, you can put a negative angle if you want that level.
Okay.
But just for
And
because some of these signs that you need to convert before you put it in that.
and you got a minus J there. Oh, but wait.
Like for
You're saying, wait a second. Oh, yeah, because now you're saying it's
cosine.
minus 100 cosine D 120 minus J 100 sine D. Yep. Mm-hmm.
So when you make the variable.
Looks good. Then you're just going to add them together.
Cool.
Convert them back into polar form. Okay.
It wouldn't be plus 30, it would be minus 60.
So it's the sine of 30 is a cosine of minus 60. Right? You had sine of 30 on that problem, right?
Yeah.
Yeah, sine of 30. Mm-hmm. So you got to turn that into cosine of minus 60, not cosine of 120.
Oh.
So did you do that thing I drew on the? Did you have this on your thing? You should
Yeah.
have that. You got it?
I got it right here. So what I did, I was just using this to get the cosine, I would get that sine at a 90 degrees to it.
Wait, cosine of 0, sine of...
Because I don't want to convert it to sine, I want to convert it to
So,
cosine.
but you had a sine. No, wait. You had the sine and you want to convert it to cosine. So the sine, when theta is 30, then this is cosine's going to be minus 60.
Oh, because I was thinking.
So, in other words, cosine of 120 would be the cosine of 120 plus 90. So it'd be 210.
Oh, that's how.
I mean, sine of 210. Yeah.
Huh. Well, that means the other one.
Yeah, that means the other ones are probably wrong too. Sorry.
Oh well.
Yeah, gotta get those.
Here's my original one current for B when I added 90 to it. And that's the same answer I got there. So it'd be S is 10, and then the angle is 110. Here, I went back and fixed it, taking a 90 out of it, and got the magnitude
30.
10.
30 minus 90 should be minus 60. Well, isn't it 30?
Oh,
It's a sine of something plus 30. Are you doing this one or another one?
oh no, I'm on B.
Oh, you're redoing B, I see.
Yeah, I'm redoing B.
So you had 10 sine of 1000t plus 20 degrees.
Hmm.
I think should see the same as 10 cosine of 1000 minus 70. Yeah. And you said when you added 90,
Yeah, when I added 90, well, I added 90 before, and then I got its magnitude. Where is it? Yeah, right here. The magnitude was 10 for this one, and then the magnitude for this one, when I subtracted 90 instead, I still get 10 for the magnitude. And here, when I get the angle, I get negative 70. But I
of
just
the
added
results,
100.
or wait, let me pause this one. I gotta dig in here and see what you're getting at. So let's see if I can articulate that. You're saying that, you know, when you added 90 for B, which, you know, is 20 degrees from
Yeah.
sine to cosine, even though I think you should subtract 90, you added 90 and got 110. Now you computed the complex number in rectangular by saying 10 cosine of 110 now, because that is what the cosine angle should be, plus j times 10 sine 110 of that phase angle. And you got that number there. Then you converted that back into polar form, and you got 10 angle 110. You said, well, yeah, I get the same answer. You got the same number you started off with, but no matter what you put here, if you put like 53 here, you would still get 53 when you came back and did the inverse transform. So it's not it's not really an error check like you're I think like you're asserting. The thing is, what happens when you add it to another like this one, when you're adding two of these things together.
Yeah.
If you have this one, if you do this where you're adding
90 to the
90 and then you redo the same problem again where you're subtracting 90, you're going to get two different results because the phase of this is going to change relative to that guy.
Okay. So it's the phase angle.
But and in one of them, it's going to be you're going to have an incorrect phase on this guy, and so the phase angle will change. And I think what would be helpful, and I should probably do this, is you know, it really helps to kind of sketch these things out. So what was the on that one that you were reading? What was the numbers again?
10 times sine.
Let me just erase some of this stuff. So you have something like 10 sine of...
1002.
I don't like it when for
No, the one where there's two numbers
the
together.
one where
When we're
there's two
adding
numbers?
two together. See, what I'm saying, this is where it's really important.
So
I mean, you're going to have an error in B as well, but it won't affect anything else if it's just, you know, that
If
one
it's just
thing.
that one.
But what about D? So D is what?
300 cosine 1000 pi t.
Okay, cosine, let's just call it omega for now,
Yeah.
plus
45 degrees.
45.
right for 3 microfarads.
Oops, and it's minus, right?
Yeah. Okay.
Yep.
So now
Minus
Minus
100 sine
100
omega t plus 30.
t plus 30. Okay. And, what we're trying to do is we're trying to add these two sine waves, right? So, 300 cosine omega t plus 45. Well, here's cosine omega t.
We'll find W.
If we have to add 45, so when we're at 0, we're really at 45 degrees, so we're kind of like here, meaning this is our point at 0. Does that make sense? So our cosine is kind of starting off here, because it sort of peaked when omega t was negative 45 here, right? And has a magnitude of 300, and then you're trying to add, or subtract this thing that's minus 100 sine omega t plus 30. Well, here's sine, right? And sine plus 30 degrees is, in other words, at t0, we're supposed to be at 30, so we're a little higher. So we're starting off like here, right? Because the sine cross 0, like at omega t equals negative 30, right?
Yeah.
And the scaling is a third of the other ones. The scale's off, but these are the two things we're trying to add together and find, and it's also negative, so this would actually be sort of flipped and divided by 3, so it'd be something like, this.
It just wants me to find the.
And we add, this and this. Well, see, if you said, oh, it's really, I'm saying this is kind of like the cosine of, God, I don't know. It's really hard to do this graphically, isn't it? It's just a big mess, isn't it?
Couldn't you just represent?
But if you're adding 90 and I'm subtracting 90, we're going to be 180 degrees out of phase for this guy, right? And so that's going to affect the summation, because in one it's going to be flipped up and the other one's going to be flipped down. So you get a different result. My point is, you have to kind of be careful how you do this so that you get the right answer.
Because when you're adding them, they're the magnitude is the same here, but that seems obvious to me now. But their direction could be different, and the direction of the vectors can affect the summation.
Exactly.
Yeah.
And an easier way to look at it, I think, is as vectors. Good thing you mentioned vectors, right? Because when we could probably sketch this better in vector space. I mean, on the complex plane. So we have 300 cosine omega t plus 45. That means 300 angle 45 degrees, right? So that means we have a magnitude of 300. Oops. Let's try doing a 45 degree angle. That's a little more like 45 degrees. Right, so that's the first component. And the second component is minus 100 sine omega t plus 30. Now again, sine is, according to this thing, sine is sort of lagging the cosine, right?
Yeah.
So that means the sine is over in this direction. And if you omega t plus 30, so if you did 30 degrees here, right? This is just a temporary, this is a 30-degree line. We would have to subtract 90 because the sine is lagging by 90 degrees. That's kind of what this thing is saying, right? The sine here, cosine has already peaked, and then 90 degrees later, the sine peaks, right?
Yeah.
And so and everything's kind of rotating this way, right? And so we are going to put, from this, supposed to be a dotted line here, we're going to go 90 degrees off, and we're going to be down here. This is going to be, we said 30, right? This is going to be should be minus 60 degrees. It's more like minus 70, but it should be minus 60 degrees. And it should have a magnitude of 100. Okay? And unfortunately, that's positive. We actually have to negate it as well if we're going to add these things together. Because we did, this is 100 sine, so this is 100 angle minus 60, which is, this, we have to subtract 90 degrees to get it into a cosine. So this becomes minus 100 cosine of omega t minus 60.
Well, yeah, I do, because I have to say.
But it's negative. And that implies either a 180 phase shift, which is the same thing as flipping this on the other side of the complex plane across the origin, right? So you're really over here. So then you get 100 angle of now it is we're adding, because we're adding 180, let's see, minus 60 plus 180 is 120, right? Angle 120. So it is adding, but because we had the minus sign there. If you added this to the 120 and then you flipped it again, then you'd be sort of double doing that. It'd be incorrect. I don't know if that makes any sense. The point is you now have two vectors, and you can add these vectors like you did in statics, and change color, and you would end up with or linear algebra, or you end up with a resultant that's over here, and this is the answer, which is going to have some new magnitude, what is it? Or just some v, yeah, this total v, and some new phase angle.
Oh, I think I forgot to. Okay, yeah.
Yeah.
So,
And then, but if you try to do it with, but if you added with the other vector up there in the bottom, then you would get a different.
If you added
magnitude.
with this guy,
Yeah. You get a different
so
result.
if we forgot to do that last thing, or if we had done it where we switched that to 120 here, because we thought we were supposed to add, so this is cosine. And then we flipped it again, then we would be back here at minus 60, and then your result would be, you'd be adding this thing to the first one, right? And so your final answer would be over here somewhere.
You bought a car in January.
Call this V air, right? And it would have a different phase angle as well. So that's the significance of
Yeah, that erroneous
making that
vector,
mistake there, yeah.
it would have a different magnitude and a different phase angle.
Right.
Not like just being in a different quadrant.
Right.
Oh, yeah, and that's the other thing too. From the arctangent function, that I just always flip it to 180. But no, but it's not true here. That A had a negative 40-degree angle.
Yeah, you don't always, and it's because you're not using the regular. I think I might have confused things. It's just when you're using the regular arctangent function on your calculator, which only takes one number.
Yeah.
That's going to be the problem. That is going to be a problem. But a negative number doesn't mean you automatically flip it.
Yeah.
What you flip is you have to have a knowledge of what the real and imaginary components are. Yeah, let me pull this thing up here again. So let me make a new one here. This is really fundamental stuff here, and I think that's the. So if what was that number again? 70 angle negative 40 or something? 170 angle minus 40, right? So this is a negative 40 degrees, and this is at a magnitude of 170, puts you over here. Nothing wrong with that.
Yeah.
All this says is that the the real part is positive and the imaginary part is negative.
Yeah.
No one says you have to flip that by 180 degrees. But if what I was trying to say is, and I said it, I guess, a little too fast, is that if you're using your calculator or just the regular arctangent function, which only takes one number, right, and you're trying to find the phase angle of a point that's over here, which is like minus 3 plus 4 I or j, let's call it j. Right, and you say, oh, I'm going to use my arctangent, right? So I know phi is the arctangent of the imaginary part over the real part, and you end up getting the arctangent of minus 1.33, right?
Yeah.
So now we just want.
Well, your calculator doesn't know what to do with that. Your calculator says, well, I know it. I can only give an answer in either this quadrant or this quadrant, and since it's negative, I'm going to give the answer in this quadrant.
Oh yeah, I already have our defined.
So your calculator is going to mislead you. And you can't just take your calculator result at face value and think that that's correct. You have to say, well, wait a second, even though, and let's actually do this. I think I did this, but let's do this again. Where's pre-mat? So in other words, we said, what's the A tan in degrees of minus 1.333? It's going to say, oh, it's minus 53 degrees. Well, you got to say, okay, minus 53 degrees. And then and you should say, oh, wait a second. That tells me it thinks that I'm over here.
I don't have a regular z variable anyway.
Yeah, and it doesn't do that.
Yeah, it doesn't.
Because you need a multiplication sign.
So we get this.
But the angle you were given wasn't in that quadrant.
But the point was actually way over here. And so you have to correlate the number that you get. So is that really negative? Well, when I know that my real part is negative, my imaginary part is positive, I can't be over in quadrant 4. I've got to be over in quadrant 2. And so you have to take that minus 53 degrees and shift by 180 degrees.
I think you just cleared up some of the confusion I've had since pre-calculus.
Yeah, so now we have 180 minus 53, which is whatever that is, and 126 I thought it was, something like that. Oops. So, and that's the angle phi that we're after, 126 degrees.
I see. Because
It's purely your
this
calculator, right? But the angle function in FreeMat is working with a complex value. And so it has the real and imaginary parts separate. So it's like it's getting two numbers.
Yeah.
And so it can keep that straight. MATLAB also has a 4-quadrant arctangent function, which is called atan2, which doesn't make any sense. But you can say atan, and it doesn't have a degree version, but atan2, you know, of this is where you give it, and I never know. I think it's y. Let me just type. No. Is there no atan2? Is it built in? We could try this out. Let's see. We know that atan2 of I think it's y comma x. It's the only one where you sort of split them. You know, it's the vertical part because it's the numerator and the denominator, right? So 1, 0 should give us pi over 2, and it does. So it's y comma x. But you can do atan2 of you know, back to our original value. You know, if y was 4 but x was minus 3, it's going to know that it's in the. It's going to know that it's in quadrant 2, so it gives you a number that's bigger than pi over 2.
I see.
But the regular atan can't figure that out because it just has a positive or negative number. Whether you're doing, you know, 4 over minus 3 or minus 4 over 3, it's going to always tell you that it's in quadrant 4.
So because in A it started out with its angle being in negative 40, then we have a negative angle.
You are at a negative angle. Just be aware of it.
So
just keep that
here,
in mind.
this has a angle that's more. This is a positive angle that has a lesser magnitude than the negative one. So I should expect an angle. I should expect a negative angle when I do the summation here.
Not necessarily, because the magnitude is going to come into play too.
Oh,
You're
that's
really
right.
adding two vectors, you know, and so you can't make those. You know, if you've done it enough, you probably could, but initially, it's not as simple as just the angles.
So I'll just check with the individual, like how I broke up C I broke up into like C1 and C2. I should check it there, then do the adding. Yeah, and that intermediary check like should take care of all of that then.
Yeah, should.
Cool.
Yeah,
Yeah.
good. Good questions. Gave me a lot of good ideas. I think it actually might make sense to actually do these, sketch these things out in the complex plane as vectors, so you can see how the addition works. It doesn't like your screen very well. Should I give up?
Shouldn't you give it a chance to focus?
Well, it usually kind of just stops adjusting at a
I'm
certain
trying to
point.
hold it still. Ah,
What happened there?
is that a? Oh, it's a tablet. That's why.
Oh, it just died.
Good job, James.
Thanks, James. You just killed the camera.
You see, remember in that scene in Jurassic Park where he just touches the computer and it goes haywire? I was like, what'd I do?
Yeah, I have that problem too. Oops, there's my face. All right. Oh, now it's in perfect focus. Maybe it was just dying. Weird. It's in better sync too.
All right, so I started here to find my V out. I did Vn is going to be equal to 4 because my angle here is
Where's
4
the problem
and 10.
again? Oh, you're doing that problem? Yeah.
Yeah, the part 4.
4 cosine
So I
d
did that for my
plus j
Vn.
times 4 times sine d. Yeah.
And then I did my V out is going to be Vn times dc. That formula that we got.
Did you determine RL? Why don't you?
So
why don't you put
so
the,
up here is my.
did you do the calculations for this?
Yes. So and these are the commands that I did to get those.
Good.
And my omega was the 60 times 2 pi, right?
Uh-huh.
Okay, so yeah, then all of these should be fairly accurate.
Very good. Yeah, that's it.
All right, great. Then we did it right.
Good.
So when you're doing MATLAB, sometimes it's hard to have confidence in your answers because you can just get a number.
Yeah.
And there was one more thing we wanted
Now
to
everyone
ask
can
you
get the answer online when they see
No,
this.
there was one more thing we wanted. So when I was calculating ZC
Mm-hmm.
for the impedance, I got this. And when it gave me my complex number, why did it give me a -0?
It's just
It's just a really small zero.
it doesn't.
Yes.
It's a very small zero.
So-
No, it's a very negative zero.
But this part, the imaginary part, though, that is my impedance for the capacitance, right?
Yeah.
Okay,
Yeah,
great.
minus 884J, and your C was 3 times 10 to the minus. Ooh, that. Yeah.
That's
right.
microfarads.
3 minus 6. Yep.
Mhm.
And L was 0.002. Yeah, good.
Can I use E notation on MATLAB, or will it think it's Euler's number?
No, E.
Okay, great.
EXP is the function to raise E to something.
Oh, okay.
Yeah.
All right, great.
Yeah, nice. Although actually, I think you can. It was very confusing. FreeMat lets you type like E. You can do E. There is the Euler's number E is in there. If you just type E on the command line, you'll get the number 2.7. MATLAB doesn't have that.
I wonder if I did.
FreeMat
Let me
does.
see 3E6 though.
No,
Oh, nice. Yeah,
That's,
that's
it
nice.
just decodes that as an exponential notation, scientific notation.
For some reason, my phone is not sending shit right now.
Good. I was kind of thinking of adding some material that would illustrate. Like this problem here, what we're trying to find is the time domain of adding these two guys together. And one thing that you could kind of do, and I don't know if this is of interest, but you could make a see what you think about this. Suppose you can I get you guys as a test audience here for a second? Like just this one thing we're adding V1 and V2 together, and V1 is 10 cosine omega t plus 45 degrees, and V2 is 5 cosine omega t plus 60 degrees. And let's just say omega is 1. And if we want to plot this, right, we could let t go from if omega is 1, when t goes from 1 to 2 pi, that's going to be a full cycle. So let's just go to 4 pi. So let's go, and we can do something called Lin space, going from 0 to 4 times pi with, say, a couple hundred points. And we've got to convert 45 degrees into, so anyway, so the first, maybe this is too complicated, but you could say, all right, so V1 is going to be 10 times the cosine of t, omega t, because omega is 1, plus, 45 degrees is just pi over 4, right? So that's your V1, right? And V2 is 5 times cosine of omega t, again, omega is 1, plus 60 degrees is just pi over 3, right?
So, are you talking about just doing it in radians, or?
No. Now we can plot these, and we can find the sum, right? So the sum equals. I think that's my mom. Let me just get this real fast. Hey, everything okay? Good. Okay. Yeah. So V sum is just V1 plus V2, right? Now you can plot these as you can plot t with V1, t with V2, and t with the sum, and you plot all three of these things on one curve. And this kind of shows you what we're doing. And I actually need to do a legend because V1, V2, V sum. Very easy to do in MATLAB, FreeMat. So these are the waveforms. So V sum is the red, and V1 is the blue, and V2 is the green. And we just added those. These is just adding the two curves together.
Right.
We didn't do the phasor thing yet.
Yeah.
Okay. But what we're saying is, and if you try to, but what we're trying to do is find this time function of the solution, right, of adding those two together, and that's really what we're trying to do. And this is difficult to do with trig identities, And we certainly don't want to do, figuring out what each point is and then adding all those time values together. That would be horrendous, right?
Yeah.
So what we do is instead is we're doing this shortcut by doing the phasor transform, converting that into a complex number, and then we are finding the magnitude. We're summing those two complex numbers together, right? It gives us 9.57, 11.440. Now we're finding the magnitude and phase of that complex sum, and then that becomes our solution. Now we can add one more plot on this curve. If I hold on, I can make an actual MATLAB? Yeah. And I can make a V calc or V sum phasor. And that's going to be this curve. We already calculated the answer. It's going to be 14.8 with a phase degree. So we're going to say, all right, well, it is equals 14.8 times cosine of, again, t, omega is 1, plus we got to convert 49.9 into radians, 49.9 times pi over 180, right? And that's going to be my V sum phasor. And actually, just so I don't overwrite the answer, maybe I can offset it by 0.001 or 0.01. So it'll be up a little bit from the V sum. And we could see they should be like right on top of each other practically, right? Does that make sense? Mm-hmm. And now I can add plot T with V sum phasor.
I'll be right back.
My target audience is leaving?
No, I'll be right back. I swear.
Doesn't make sense. And you can see they are right on top of each other, right?
Yeah.
That's showing you the validity of the phasor method. It's a shortcut way to get the sum of two phasors or some other mathematical operation. Once you have this, makes it really convenient. So I think that's because a lot of times we're not really sure what we're doing, and the phase angle really is another mystery. I think a lot of it just takes a while to kind of get comfortable with what that is. If I put this into Paint, what the phase angle really represents is, oh, my pen's over there. It's kind of like the starting point, right? In other words, at t0, this is kind of where all these guys are starting, and that's the V sum, right? So this is 14.8. Oops, we don't need the parentheses there. 14.8 times the cosine. Well, when t is 0, what's the phase argument? Well, it's just 49.9, right? It's just a starting point, and this is our V1, which I think is 10 cosine of 45 degrees, right? And so it's the starting point. This is 5 cosine of 30 degrees of where these things are beginning. And the phase, if the phase angle shifts, then the whole thing is going to shift left or right, right? If you increase the phase angle here to say 60, it's shifting right then, because it's getting, no, cosine's getting small. Wait. Actually, if it's 60, it's getting, cosine of 60 is bigger than the cosine of 49, so it's going to get bigger. So I guess it's shifting, yeah, it's shifting the curve to the right as the phase gets bigger. So anyway, that's sort of what's happening, kind of. But I think I will probably in a future lab maybe incorporate some of this stuff in there so it's a little more concrete. Really comes down to these sinusoidal oscillations that we're trying to model. We're modeling these with complex numbers. Hope that makes sense. In case you're wondering why we're doing this. Okay, target audience, any feedback? The remaining target audience? Any questions on that?
Yeah, so the angle, like 49.9, right?
Yep.
That shifts the graph of the to be sum
Mhm.
to right or left, right? Is that what it does?
Yeah, if that phase angle was different, then the whole thing would shift to the right or to the left. Yeah, what the phase angle is doing is kind of showing us where it's shifting relative to the other ones.
Okay.
If they all had a phase angle of 0, then they would all be, you can see the discrepancy between these guys, the peaks here, and we could probably read something into that either, too, right? Because, right, actually, it kind of makes sense when you see these three peaks, that this peak, which is a peak of, the 49-degree peak, is a little bit to the left of this peak, which is the 60-degree peak, which is both of these are to the right of this peak, which is 30, right? So this is saying this is your 30-degree peak, this is your 49.9 peak, and this is your 60 peak. So as the phase gets bigger, the thing is kind of shifting to the right. And they're all, they're fairly closely aligned, but they're a little bit off. And that affects the result, right? If they are 180 degrees out of phase, then the result is going to be completely different. Yeah, anyway, hope that helps.